Hey Physics 30s, how's it going? So we are going to do our de Broglie practice questions here. So remember, de Broglie is all about the wave-particle duality of matter and energy and photons and things without mass and things with mass. It's all kind of crazy. But here's an electron that's moving at 200,000 meters per second. What is its wavelength? Okay, so all de Broglie said is rather than saying the momentum of a photon is based on its wavelength, then you can also say the wavelength of matter is based on its momentum. So you just rearrange this formula that said P is equal to H over lambda. Now it's lambda is equal to H over P. And since we have mass and we have a velocity here, we can find our momentum by going m times v. Okay. So I'm going to use my, well, I'm not going to bother typing anything in here or write anything out here. It's just going to be the 6.36 number, 6.63 number, sorry. I'm going to divide it by the mass of an electron. Time also divided by the 20,000 meters per second at the same time. And I get 3.64 times 10 to the negative 8 meters. There you go. It's actually a pretty high wavelength there. What's the momentum of a photon? Well, the photon calculation is the exact same formula. This time we have the wavelength, so we just use this number. Which is the joule second version. And divide it by this number, the wavelength in meters. Set that my calculator. And I get 1.33 times 10 to the negative 27 kilogram meters per second. There we go. Cool. What is in your TV set? This is the old type of TV set. An electron is accelerated through a potential difference of 21,000 volts, very similar to the one above it, or maybe close to it. How much energy does the electron acquire, and what's the wavelength of this electron at this energy? Okay, so we are going to use, I'm going to make a couple assumptions about the electron's initial velocity. Let's say it's 0. So I'm going to want to find out using this. I'm going to have to find out how fast it's going. I'm going to have to find its final velocity. Because then I can use that to find its momentum. Okay. If I can find its momentum, then I can find its energy, or I can just find its wavelength. Okay. I guess I can find its energy as well, but the energy part is going to use the kinetic energy, but then I can use its momentum to find its wavelength. H over momentum. So that's my goal, is to get to there, right? So the first part, what I'm going to want to do is find the energy, in this case, the kinetic energy. Okay. So I could do that by going up to my formulas here and say, oh, the change in voltage is equal to the change of energy. Remember, this energy could be either potential or kinetic. Because we're talking about kinetic, I should say I am losing potential and gaining kinetic. So my change in energy is going to be my voltage times my Q. So 21,000 times the 1.6, because it's an electron, right? Yeah. Let's highlight that. Okay. I'm actually going to write this down then. 21,000 volts times 1.6 times 10 to the negative 19 coulombs. And we get an energy in joules, a change of energy specifically, of 3.36 times 10 to the negative 15 joules. Cool. Now, because this is going to be final minus initial, and initial is 0, this is my final kinetic energy. Okay? Now, what I'm going to do now is I'm going to use that final kinetic energy in part B here. So this is all part A. I'm going to write here. Okay, so that's all part A. So I'm going to use that EK that we found here, 3.36 times 10 to the negative 15 joules. And I'm going to go 1/2 mv squared. I'm going to rearrange that to find how fast this electron's going. So 2 times this number divided by my mass, my electron. Take the square root. It's going pretty fast there. 8.588 dot 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 times 10 to the 1, 2, 3, 4, 5, 6, 7. Ooh, super fast. Fast. 7? Yeah, 7. Okay. So now we know how fast it's going. So now I can use that to find its momentum. Mass times velocity. So I'm going to take that number times it by its momentum, or its mass, sorry. And I'm going to get 7.824 times 10 to the negative 23 kilogram meters per second. Now, I'm going to use that momentum to find its wavelength. Here we go. .47 times 10 to the negative 12 meters. It's quite small, right? That's well within like the X-ray to gamma ray range of wavelengths. So we could use this like an electron scanning microscope to get a higher resolution of image. Go way down into almost, this is like not a femtometer, but down to a picometer in size. But if you get even higher energetic electrons through particle accelerators, you definitely do that. If you get down to the femtoatometer range, you can see the atomic structure of atoms, right, based on the reflection of those wavelengths off those surfaces. Hopefully you did well in this worksheet, and I'll see you in the next video. Bye. I can't stop.